Good morning, everyone. Today we have the pleasure to have Violetta Sagun from University of Coimbra, and we're going to hear about astrophysics, dark matter, and neutron stars. So, please, Violetta.
Thank you very much. Please stop me in any moment to ask questions. It's better to clarify during the talk. Questions. So I'm going to talk about compact stars and the question of dark matter and how to probe dark matter within compact stars. And in the beginning, probably I will talk a little bit about some basic properties of compact stars, especially neutron stars. Then I will focus on the accumulation of dark matter, how compact stars will accumulate dark matter. And after that, I will present some effects of dark matter on compact stars. For example, how mass and radius of compact stars are modifying tidal probabilities and waveform. And also, I will talk a little bit about neutron star cooling or heating. Then I will present one model of fermionic dark matter and one model of bosonic dark matter, with the following application to numerical relativity simulations and how compact star would affect merger dynamics and merging of compact stars. And then we'll give conclusions. So compact stars, they're really compact. They basically have the size of municipality Conselho de Aveiro, and as you understand, it's super dense and super small. The mass of compact stars between 1 and 2 solar masses, with a density that is exceeding the density of void-dwarfs and many orders of magnitude. So compact stars, they're very extreme emitters of the central density, of the rotation speed. So the equatorial speed could reach half of the speed of light. In terms of the magnetic field, the magnetic field can reach 10 to the 16 Gauss. And also temperature in comparison to temperature void-dwarfs and sun. But we treat with very good approximation compact stars to be at 0 temperature, which is a very good approximation. And with this approximation, we also consider different content of the compact stars. So when I'm saying compact stars, basically I could refer to all this kind of stars. So, but if I want to specify it with just neutrons, protons, electrons, and muons, and set in compact star, then I will refer to the star as a neutron star, which is like a normal star, normal compact star. Then I can consider some condensates of pion and chaos. Then we will refer to the compact star as a pion condensate. Inside, in the core, could be some heavy baryons, some lambda, delta, and so on, as well as the phase transition to quark plasma. So then we have a core of quark plasma, or we could have a strange star, so star made of quark plasma itself. Today I will focus only on neutron stars, but basically the same dark matter related stuff could be applied to strange stars, hybrid stars with quantum plasma core, and so on. But so far I will use the introduction to the compact star neutron stars and application to the dark matter topic. So how we start to model compact stars? We start from the equation of state. The equation of state is some relation between, say, pressure and density of pressure and mechanical potential. So relation between different thermodynamical quantities. Having the equation of state, we use it like input to the Tolman-Vergeben-Walker equation, and we get the mass radius curves. So each of the mass radius curve corresponds to one of the equation of state. And nowadays, due to uncertainties of the properties of strong interact method high density, we are not sure about high density. So that's why we see a lot of different equations of state. But the idea is that between the realistic equation of state give the radius of compact star between 11 and 13 kilometers. So this is the range of the radius between 11 and 13 kilometers. And from astrophysical side, we also have constraints on the maximum mass. So as I will talk a little bit after. We have already 4 stars with mass above 2 solar masses. So the realistic equation of state should reproduce at least 2 solar masses. So this should reach into this point. If, for example, any curve, let's say that it is blue one, is not reaching 2 solar mass, it's not realistic equation of state, it's not reproducing astrophysically. But on top of this, so the compact stars, because they are compact, because space-time, they could accumulate sizable amount of dark matter in the atmosphere. That could also alter the properties of the compact stars. So we could not consider compact stars to be kind of in a vacuum. Compact stars existing in dark matter, and depending on the position of this compact star in the galaxy, the compact star could accumulate different amount of dark matter. So here I did like a summary of different accumulation regimes. In the beginning, we believed that during the star formation stage was already the mixture between the dark matter and the baryonic matter, so protostar already included some amount of dark matter. Then during the main sequence star, also we can calculate more or less the amount of dark matter, captured dark matter, which is 10 to the minus 5 and to the minus 8 solar or 9 solar masses in the most central part of our galaxy. The next stage, the supernova explosion and formation of the proto-neutron star is quite unknown. We don't know what is happening during supernova explosion. Dark matter could be created due to the explosion and shock waves, but there are no estimation of amount of dark matter created during this stage. And then during the stage of a Coimbra neutron star, we also can estimate the amount of accreted dark matter. And the value is more or less the same as the minus 38 solar masses.
Sorry, 1 second. It's technical thing. And maybe I should start screen sharing, otherwise I don't see anything in the chat.
Do they complain or?
Should I start?
I just received a message. Sorry, guys.
Okay, so then I'm always saying in the most central part of the galaxy. Why it's so important? Because there are profiles of dark matter in our galaxy. For example, this is the 2 plots for a master profile. Also, there is an Navarro-Frank white profile. So in the central part of the galaxy, the density of dark matter is many orders of magnitude higher than, for example, in the vicinity of the sun. And that's why accumulation of dark matter in the most central part of the galaxy is much more efficient than, for example, next to the sun. So that's why all these estimations were made for the most central part of our galaxy. Depending on the nature of dark matter, it could be accumulated either in the core of the star. So it basically will sink down and be accumulated in the core, or it could create a very dilute and extended halo around the compact star. And depending on the nature of dark matter, we would see a different effect on the compact star properties. So, for example, in the case of the dark matter halo, we would see a decrease of the maximum mass and the observed stellar radius. And in this plot, you can see different equation of state. So all these curves correspond to the realistic equation of state. The solid curve corresponds to pure baryonic equation of state. And dash one is dark matter mixed compact star with 5% of dark matter. So you can see that having 5% of dark matter in the core, we see a reduction in the mass and radius for the compact stars.
Which are the properties of the dark matter that you use to create these star solutions, these mixed solutions?
Yeah, so I will show after that basically you will see the same trend for fermionic and for bosonic dark matter. Absolutely the same.
So why did you choose 5% there? It's just an illustration.
It's just an illustration. It's not my paper. It's from this paper, but I will show it after my results. It just gives you an idea. 5% is just something that's it's invisible, so it's quite a big amount of dark matter. 5%. And the effect is visible. So to illustrate the effect, it's good to consider kind of big amount of dark matter. But in case of the dark matter halo, we would see completely opposite behavior. So then we will see an increase of the maximum mass and the outermost radius. So outermost radius, in the case, I will go back. So if we have a halo, basically our compact star is embedded into the cocoon of dark matter. And then the outermost radius will correspond to the radius of the dark matter component, while the baryonic radius would stay the same. So we would still see the same baryonic star with diameter of 24 kilometers, but this baryonic star will be embedded in invisible dark matter. That's why in the case of dark matter core, outermost radius will correspond to the radius of the baryonic component. Yeah. But in the case of the dark matter halo, outermost radius will correspond to the radius of the dark matter component. Outermost radius will be different.
Can I ask a question about it? So you said that the baryonic star radius, so the baryonic core will stay the same in the case of the halo, but if you put enough matter in the halo, wouldn't you expect that there's going to be enough pressure so that it can compress a bit more the baryonic core? Does it happen, or is there kind of, I mean, if you put 50% of the mass in the halo and 50% in the baryonic core, will it decompress a bit more?
So what we see that the halo is created for light dark matter particle or dark matter particles with strong repulsion. And then you cannot compress because dark matter has its own repulsion. So it's self-repulsive.
Right, but it has its own weight as well.
Yeah. So gravitational, they interact for sure. They gravitational and they change the energy density distribution of the baryonic component. Absolutely.
But it doesn't change the radius, that's what you said.
So it's not changing drastically. Halo is not changing drastically the internal composition.
Right. But probably it depends on the fraction of dark matter versus one of baryonic matter, of course.
Yeah, but what we also see for halo, again, halo is light particles or particles with strong repulsion. It will increase more the halo, so the size of the halo, but it's not like accumulating in the.
You show us more results.
Yeah.
Good.
So if we know that the dark matter interacts with gravity, and we have some upper limit on the interaction of other interactions, but if we model mass, radius, mobility for the compact stars, we can completely forget about any interaction except gravitational. And in this case, we can split the Tolman-Volkov equation for two equations. With the difference that pressure would be the total pressure of the system and mass would be the total mass of the system. And in this case, we also could say the fraction, define the fraction of dark matter, which is the mass of the dark matter component divided by the total mass of the system. This is how we define our fraction. And on this slide here, you can see different equations of state. As I said, we have we don't know about the baryonic matter high density. That's why we consider the IC equation of state a little bit softer equation of state. So by softer, I mean that the pressure is not growing so fast with the density. And a little bit steeper equation of state, DD2, which means the pressure rises much faster. And on top of this baryonic matter equation of state, we added 1, 3, and 5% of dark matter. So here you can see that having more dark matter equation of state makes it become softer. Again, I'm using this term of nuclear physics. So your pressure, you make more compact stars. So the more dark matter you add, the more compact configuration you create. And that's why your tidal deformability is decreasing. You see a decrease of tidal deformability with increase of the fraction of dark matter. So tidal deformability depends on the total mass. The more dark matter you have, the more total mass you have. And the outermost radius. And as I said before, the outermost radius will be different in the case of dark matter core and dark matter halo configuration. That's why having dark matter core, we always make compact star more compact. In the case of the halo, because of this huge value of the outermost radius, our tidal deformability is skyrocketing. I will show after how big they are. Do you have a question? No?
Actually, yes.
Yeah.
So you are treating the dark matter also as a fluid, right?
Yes, the second fluid.
Okay, what is the equation of state for that fluid?
So this result is for baryonic dark matter. No, this is for bosonic. But after I will show two models, harmonic and bosonic. Another effect of dark matter is the gravitational waveform. So people did the preliminary calculation of the dark matter to be condensed in the core, and they saw that presence of dark matter in the core might produce a supplementary peak in the characteristic gravitational waveform. So, for example, without dark matter, we will see only F1 and F2 and F3, three peaks that comes through from the baryonic matter component. And due to the presence of dark matter, we will have one additional peak, which is not present in the case of the baryonic star. And this result is for equal mass system. And in case of the unequal mass binary system, we would see two additional peaks due to the presence of dark matter.
Yes, so in these mergers, are you forming a black hole at the end?
Depends on the mass.
Right, that's exactly. But these ones that you're showing there.
So this was post-Newtonian calculations. So it was.
That's their full gravitational waves.
It's the sum of the two.
So I suggest to wait until the last numerical simulation. I will show you different mass difference. So it will we did the real simulations, and then depending on the mass and the fraction of dark matter, we saw also different results. For some, it was created the hypermassive neutron star. For another configurations, we had collapse to the black hole.
So, but understand, so you said that there is an extra peak because of dark matter, but this occurs after they touch, or are you talking about still the
So this is
the
the core.
inspiral?
This is a core configuration.
Right.
Yes, this is the core configuration. And when they touch, and already after the merger, yeah.
Right, and you're using just post-Newtonian to when they touch?
No.
No.
So in this, I think this calculation started with the post-Newtonian. But what we did after, so I will show you here the results of two fluid numerical relativity simulation with solving initial conditions, with solving everything. But this was just the preliminary result from, I think it's from 2019 in this paper. It was just first results coming that the effect of dark matter could be visible in the gravitational waveform.
Right.
So it was results from 3 years
The
ago.
paper by Bezares at all is
I think-
not a numerical relativity simulation.
I'm not sure. Or this is the reports from Ellis or from Bezares. Bezares is numerical relativity.
Fully numerical relativity.
Yeah, but they didn't solve the initial conditions for, as I remember, they didn't solve initial conditions for dark matter and compact stars.
Right, so
So they just imposed.
they superpose the
Yeah.
two stars, which is okay. Yeah, but I'm wondering more about the end, because I could not see there a distinct pattern of black hole formation going down. So I was wondering if you, or just a hypermassive star that would relax to some sort of star, or if you would be forming a black hole. But anyway, you
But
show us more.
for my results, I'm not
Let's keep going.
Can I just ask a question? So is there any special with the interpretation? I'm just curious about these different peaks. Do they have a special interpretation?
Like I'm not GR person, I'm a nuclear physicist.
Okay. Because you mentioned that at least for the first plot, so you have an extra.
Yes, I know. So in the post merger phase, probably should be a question for you. In the post merger phase, you could probe the interior composition. So these peaks should be related to the interior composition of the complex. But how exactly? I cannot answer this question.
So what exactly are you plotting there in the vertical axis? So that's, there's so many things.
I have to go to Alice and see.
And this is a spectral thing, right? So it's in terms of the frequency. So yeah, it's kind of this triangle. Yeah, so you see several frequencies, peak frequencies. Yeah.
There is a picture.
Anyway, okay.
Another effect of dark matter is related to the heating or cooling of complex stars. And it depends whether or not the dark matter particle is symmetric or asymmetric particle. By asymmetric, it means that there is no particle-to-particle annihilation, and then dark matter could be accumulated inside the star. And then, of course, we have two scenarios, whether it's a fermionic dark matter or it's a bosonic dark matter. In the case of the fermionic dark matter, Pauli blocking may prevent the collapse of the black hole. So basically, Pauli pressure is enough to sustain the gravitational force. But in case of the bosonic dark matter, at zero temperature, bosons form Bose-Einstein condensates that could eventually collapse to the black hole. So to have dark matter accumulated in the core, you need to add some self-interactions, you need to add some repulsion between the dark matter particles. But at the same time, the models of asymmetric dark matter should allow all neutron stars to exist. It means that if some fraction of dark matter, the star would overpass the Chandrasekhar limit and would eventually collapse, we would not see all stars. But in fact, we see all the neutron stars that to the 6 and to the 7 years. So the collapse is not happening. So that's why it gives us the constraints on the repulsion between the particles.
I'm being sorry to interrupt you all the time, but I'm just curious, Jane. So how do you estimate the age? So you said that you see these old stars.
Let me then go. Yes. So these are the experimental data. All this 18 data points experimental data. We could plot the temperature or luminosity of photons or neutrinos for the function of the age. So we have stars that to the 6 and to the 7 years. These are the most old neutron stars. It's part of the plot, the most old neutron star that we see.
So the curves there are from theoretical models.
Yes,
for
these are
different-
moving curves that, yes, I will
Questions
show.
of state.
But now I want just to focus on this experimental data. So we have the oldest neutron star that we have is down to the 6 years. So for example, the interesting object is number 0, and this supernova 1987. So number 0 is a Cassiopeia A, so it's the object that is 340 years old. And it was written by, I think, by the Arabs. It was written that it was the bright star appearing on the sky, so people knew where to look at, but in the beginning it was covered by the dust. And we saw this object only like around 20 years ago, because all this interstellar neutron started just to extend, and we saw that this is a real neutron star, so it's not a white dwarf. Another object is the supernova 1997. Again, it was a supernova explosion. And until recently, I think the object we saw this only 2 years ago, before it was also covered by the dust and everything. And now we see that this is the neutron star. So what people look, they look basically on this expanding dust interstellar medium, and they try to just go back and see more or less when there was the supernova explosion. That's why the error bars are kind of big, because you can go back, but you cannot go back precisely when the star is exploded 10 to the 6 years ago. In case of symmetry between particle and antiparticle, there will be an annihilation of dark matter particles and antiparticles inside the star, and then it will create additional heating. For example, if dark matter particles could annihilate, they would heat up the star, and we could see this as an X-ray, a gamma ray, or some neutrino telescopes. So most of the models give us late-time heating. It means that the higher surface temperature will be visible for the old neutron stars. And what we see is we see some cooling of the neutron star, and after that, additional heating that appears due to the interaction of the complex stars. But to understand this, let's first move on to the equation for the thermal balance. Basically, compact stars, they cool down by the emission of neutrinos from all the volume of the star, and also emission of photons from the surface of the compact star. In case of any additional mechanism, let's say annihilation of dark matter or something, you'll have a one term which goes here with the opposite sign with a plus. It will be heating, and minus it would be additional cooling mechanism. And on the left-hand side, we have a total heat capacity multiplied by the change of the surface temperature, from the distant observer. Basically, if you have a dark matter, you could contribute as an additional term that matter could heat star without the star or be a like additional cooling mechanism. And we would see this in the cooling curves. So this on the right plot, you can see different cooling curves. What we need to fix, we need to fix the mass. So different curves for different mass of the star. And also you need to fix the equation of state. Obviously, the equation of state defines your particle composition. And after that, as we don't know the chemical composition of the atmosphere, we have to model a little bit like the atmosphere, made from hydrogen and helium. This is the upper set of curves. And a little bit heavy element atmosphere made from carbon, oxygen, and so on. That's why you have the second set of curves. And also, depending on the chemical composition on the particle, we have different processes going on. So the blue curves, this so-called standard cooling or minimal cooling. It's when you have just Brunststrahlung or modified Lucas process. Modified Lucas process basically just the decay with participating neutron and proton. That's why it's modified. So it's modified by the medium. Then you will see kind of light cooling, so it will be very slow cooling. Then if you have some additional particles, let's say some condensate or superfluidity, superconductivity, then cooling curves will go here in the middle part, and we will see some intermediate cooling. In the case of quantum plasma or direct Lucas process, we will see this fast drop of the temperature, and then a little bit slower cooling process. So depending on the internal composition, you could see different cooling going on. And anything that matter could affect this. So how that matter could be created inside the complex stars. For example, people from this paper, they consider nucleon Brunststrahlung. So that matter is created in the nucleon Brunststrahlung or by Cooper pair breaking information process. And then we will see the modification of the cooling curves. So for example, in this paper, in these basic two papers of Sagun, he considered axions that take out energy. So axions in this case would cool down the star because they would be emitted from the star. He considered different coupling constant of axions using nuclear matter, and he saw that we see modifications of the cooling curves for medium and all neutron stars. For very young neutron stars, basically we don't see the effect so much. And as I said, another possibility, another effect of dark matter is heating. In this case, dark matter should annihilate inside the star and create this change of the cooling curve due to the annihilation. Or we could see this effect in our galaxy if we look more to the center of galaxy. So I said in the beginning of the presentation that in the most central part of the galaxy, we have dark matter content much bigger than in the sun, vicinity of the sun. The closer we go to the galaxy center, to that red, green, and blue, the bigger the fraction of dark matter. So the dark matter is annihilated much more intense in the star. That's why we will see bigger effect of late-time heating of compact stars in comparison to, for example, compact stars in the sun vicinity. And let's move on to another effect of dark matter, which is related to the mass, radius, and time of the formation. In this study, we considered fermionic dark matter, very simplified, like vanilla case, when the dark matter was modeled as relativistic Fermi gas with spin 1/2. For the baryonic component, we considered the realistic equation of state that reproduced all the nuclear matter properties, high energy physics, and astrophysical constraints. And we started how dark matter affects mass and radius. So we have the 4 stars with mass above 2 solar masses. And then that means the dark matter, these compact stars should reproduce these 4 observations, 4 data of compact stars. of course, we have to consider different mass and different fraction. That's why we look on the kind of light dark matter particle with mass 100 MeV and the heavy dark matter particle with mass 1 J. So what we saw that for light dark matter particle, we see an increase of the maximum mass. And for heavy dark matter particle, we see a decrease. The higher the diffraction of dark matter, the lower the mass and the more compact the star itself.
So, are these curves for spherical stars or are they rotating?
No, they without rotation.
Without, and the rotation, does it impact significantly with the star type of curve?
Yeah, usually rotation adds like 10-15% to the mass.
Adds.
And yeah, it will increase.
Can you provide the dark matter mass beyond these ranges above and below? Here, in the edge of likely.
We started from 100 MeV. We can go a little bit lower, but again, it will be too big halos.
Yes.
So, for example, here I want to show that the light dark particle, you can see that 1% of dark matter, the radius of dark matter component was twice the radius of the bionic component. And for 3%, we have a radius of dark matter halo 135 kilometers. So if we would consider even lower than 100 MeV, the radius of the dark matter halo would be huge. Huge.
So this can be like a stellar neutrinos. This is fermionic phase, right?
Yeah, it's a fermionic, but as I know, many neutrinos could not go to so high. So,
No, stellar neutrinos.
Ah,
They
stellar.
can be. Yes.
so in case of the core configuration, you see that the heavy dark matter particle tend to condensate. So to see this, we plotted the energy density as a function of the radius for two components separately. So you can see that the dark matter component vanishes at 100 meters, and the bionic matter component continues until 11 kilometers. So from this, we see that the dark matter component creates this very dense, small, compact core. And then the bionic component continues until more than 10 kilometers radius. And for halo configuration, we have this tail, so the big values. We see this effect also in diode deformabilities. So here you can see also core configuration and the halo configuration. If we plot the diode deformabilities, we see that core configuration will stay softer, so more compact star. In case of the halo, the diode deformabilities they grow very much, and at certain value they cannot reproduce GW17 or 17 anymore. And that's why we say that the first neutron star to star merger event, GW17 is not in agreement with the big halo configuration. Small until several kilometers, yes. Also, we wanted to study what is the critical fraction where still we can reproduce to solar mass limit. So what we did was the maximum mass of the function of the fraction and the different mass of dark matter particles. So what we saw that for 100 MeV, we're always in agreement with the solar mass constraint. So we're always above 2 solar masses. For 174 MeV, we are exactly at the limit with the curve touches 2 solar masses and start to rise again. So it means that for 174 MeV, we always in agreement with 2 solar mass constraint. And then for heavy mass particle like 1 J, we're in agreement with 2 solar mass constraints only up to some values like 4%. And from this, we can put a constraint on the dark matter, on dark matter mass. So we can plot fraction of dark matter as a function of the mass of dark matter particles. Fix this 2 solar mass limit. So this on this black curve, the maximum mass equal exactly to 2 solar masses. Then below this region is an allowed region, and the mass is above 2 solar mass for any fraction from this range and any mass of dark matter particle. And above this curve, it's a not allowed region where we cannot support 2 solar masses. Also, we plotted here the diode deformability constraint from GW17, and we see that this area here is in agreement with both astrophysical constraints for 2 solar masses and neutron star merger. But after that, how we could fix the fraction? Because we have two parameters, we have fraction and we have mass. To fix fraction, we did estimation
Sorry,
of the.
can I ask one question? Just to understand better that thought. Is that for a specific equation of state there?
Yes.
Which one?
Yeah, it was that one that I showed.
The ISG.
Of course, it will change. There will be a little bit different equation of state, the curve will be a little bit shifted.
Yeah, the quality is.
Yeah. It's going to change.
So you use not having model like still assuming that there is no like photo keys and all. So like the only interaction you have here is still going to be.
Yeah.
So like for instance, in plot, if there is this some like fixed photo to dark matter or any type of photo, would the like, constraint be stronger
It
or?
will change. It will change. It depends what kind of would it be attraction or would it be repulsion? Like what would be what kind of attraction would it be? To fix one of the values, we did an estimation of the amount of accumulated dark matter in the most central part of the galaxy for main sequence star stage and neutron star stage, what I showed in the very beginning. And we calculated that in the most central part of the galaxy, the fraction accumulation of these two stages could be 0.01%. So that's why we plotted here like a horizontal line. And then we look around the cross with this horizontal line with the black curve. So it gives us the constraint on the mass of the dark matter particle, that upper constraint. So it means that if in the most central part of the galaxy we'll find a star with two solar masses, it will automatically give us constraint on the mass of the dark matter particle to be below 60 J. Again, this goes for the most central part of the galaxy. But to give a more precise constraint, we need to calculate the accumulation regimes during other stages, like supernova explosions. Also, it's just the preliminary calculations. Also, with this model, we can answer can try to answer the question: what was the secondary component of GW-0814? So this was the merger between the black hole and another secondary object with the mass 2.6 solar masses. So the mass of the black hole was 23 solar masses, and the secondary component was 2.6 solar mass. But I showed you the mass radius plots in the beginning, and I said that the realistic equation of state should reach two solar masses. And most of the realistic equation of state would reproduce only 2.1, 2.15. They do not go to 2.6. This is the big problem. That baryonic equation of state could not support 2.6 solar masses. And this mass was like in so-called mass gap between where the compact star finished and the black hole still lived. We didn't have any observable black holes this mass. So then there was a big debate: what was the origin of this object? Was it still a compact star, or was it the very light black hole? As baryonic equation of state could not support 2.6 solar masses, people start to propose some exotic degrees of freedom, some early deconfinement by transition, super high speed neutron star. This answers your question. So with super high speed, you could try to reach 2.6. If you have equation of state, let's say 2.3, with spin you can reach 2.6. You can get a little bit of mass. There also people propose some extra steepening at very high densities for baryonic equation of state. But as an alternative explanation, it could be dark matter and mixed complex stars. And just like a simple vanilla model, I tried to use this fermionic non-interacting dark matter equation of state to reproduce 2.6 solar mass, and we can do it with the 23% of dark matter. And of course, this is the Halo configuration because Halo increases the mass. So the idea is that with dark matter and mixed compact stars, we could reproduce 2.6 solar mass object to be a compact star, but also if it's the black hole from the mass gap, this object could also understand the formation of sunlight black hole. So, for example, a formation of the black hole could be due to a collapse of black matter compact stars. So this dark mixed idea is able to reproduce this secondary object to be like a star or very light black hole.
I can ask a question about, so here you're increasing the mass by putting in the halo, if I understood
Yes.
correctly. Now, the halo should leave an imprint in the waveform. And well, this has been known for some time, we've actually referred to it also in the context of 70. But if you have this halo, so then you'd expect the frequency of the merger to be smaller, for instance, because they touch somehow when they're still further away. So there should be a clear imprint. Well, I'm not sure how clear it would be, but my question is that people look into the mergers of these objects, so neutron stars and halos and black holes, to assess the extent to which the halo size can impact on the wave. And in particular, I mean, just say the frequency at which the peak of the signal occurs. Do you know if this has been
So far, like of your collaboration, they don't consider dark matter. So you have they consider mergers to be kind of in the vacuum.
Sure, but
And what
for
they
their
do?
subject, I was asking more from the theoretical view, but there are groups doing this sort of. I know there are some groups doing mergers of neutron stars, of course, with black holes,
Mhm.
but I'm not sure how much has been done in putting, this kind of halos around neutron stars.
So that's what we are doing.
Okay.
Yes, our idea
Very
was
good.
to change, was to show to like the people that mergers they occur not in the vacuum, that there is a medium, and then the medium is a dark matter, and we have to model everything. We have to model core configuration for different particle mass. We have to model halo configuration to create the waveforms, and to use these waveforms when they have like a signal, to use it in between the to increase the database with these templates. So far, there are no templates.
Mhm.
And for this, to create these templates, people have to do numerical relativity simulation with solving initial condition, with everything. So this is the first. You have to do a lot of merge simulation to create the templates that give to like your people. So this is what we started to do, and I will show you just the first result in the beginning. But but we are working on this. So one more very briefly model of the bosonic dark matter. So what we created, we consider the bosonic dark matter with self-repulsion. So we consider the vector field in the mean approximation that gives us repulsion at 0 temperature. So we would not have a collapse to the black hole. And on this plot, you see one Jeff particle. For different equation state, again, for a little bit softer, a little bit steeper equation state, and the same fraction, 1, 3, and 5% of dark matter. All this experimental data here, 1.4 solar masses from NICER. It's a X-ray telescope that measure mass and radius simultaneously. These three horizontal lines, the measurements of the massive pulsars. And the contour plot, the 2 solar mass is also a second star observed by NICER, also simultaneous measurement of mass and radius. And this two data is GW17017 and 19045. Neutron to star mergers.
Yeah, I was just looking at the Lagrangian. So you have a complex scalar with a mass, and then you have a real vector that also has a mass term, right?
Yes.
So what's your motivation? Have you been working up on that scalar to do that?
Yeah, our motivation is just to prevent collapse of the bosonic dark matter to the black hole. So to add repulsion to dark matter. And then, when we could see that the vector field, we have this additional term interaction, basically, which we also play with the interaction. So in the previous, when I showed the Fermi dark matter, we had only mass and fraction, we had 2 parameters. of dark matter. In this model, we have one more parameter comes from the interaction scale. So we this interaction scale is defined like a mass of the vector measure divided by the coupling constant. And then we write the interaction scale and the mass and the fraction to see the interplay of the parameters and the effect.
So you're talking about the repulsion. Where is the repulsion coming from? So the dark matter is complex scale.
Yes.
Here.
Yes, and then the vector over the field gives us repulsion.
You could also get repulsion by putting a quartic interaction
Lambda feet on the force.
on kind of the complex
Ah,
scale.
the
If you
complex
put a kind of fourth, that will also give you a repulsion. There's several ways.
Yeah.
Without kind of gauging it, but you gauge it with a massive vector field,
Yes.
so it's not really.
It's an H. It's an H.
But there's no gauge varies. Gauge broken gauge varies quite much.
Yes.
And we also considered, we also look on the profiles of that method. So this is an example again of the energy density profiles of dimensional pages for baryonic and for that component separately. So what we saw that for one jet particle, we have again the super dense core with radius around 2 kilometers, and then the baryonic star continues at 12 kilometers. So we saw the same behaviors for fermionic dark matter. And also as a first step, so as I said, we are now working with numerical relativity simulation for the core and for Halo configuration. So with all the initial conditions, the real numerical relativity calculations. But the first step was to consider kind of a simplified model for dark matter, zero dark matter. And in this case, we didn't solve the initial condition, we superimposed them. It was just the first step to see, to really understand the effect of dark matter. For baryonic component, we considered the SOY equation state. Also, we considered 1.4, 1.3, 1.2 solar mass stars, and 0.5 and 10% of dark matter. So in there we have 9 configurations, different combinations of the mass and the dark matter fraction, and we performed the mergers. On this right plot, you can see the distribution of baryonic matter in the color and distribution of dark matter as a contact plot. So you see the dark matter creates the core configuration, and after merger, dark matter again still condensed in the core. And then basically the conclusion that we got, that the higher dark matter fraction, the longer the spiral, which is likely due to the lower deformability of dark matter. And also we saw different patterns of the waveform. We saw collapse to the black hole, and we saw the long-living hypermassive neutron stars. So 1.2, 1.2 solar masses, we saw for 5 and 0% of dark matter, hypermassive neutron stars. For 10%, it was collapsed to the black hole. For higher mass configuration, for 1.3, 1.4 solar masses, we saw collapse to the black hole. And the explanation for this is that dark matter, again, is dark matter co-configuration. So co-configuration from a favored collapse to the black hole. We expect if we would model the Halo configuration, we would not see collapse. So it's the co-configuration in favors the black hole. Also, we didn't see any ejecta of dark matter, so ejecta only of the baryonic component. Again, we believe it's due to the compactness of the dark matter core. And also we saw the decrease of this class with increasing of the dark matter fraction. So this is our results, and they were just a first preliminary step. So now we consider fermionic dark matter to be in the core and also in the halo. So basically, the first model, this equation of state that I showed. Now running numerical relativity simulations for different masses, fractions, and so on. The new results will come soon. And this. Let me conclude. I showed you that dark matter can be accumulated in the core, and in this case, we will see a significant decrease of the maximum mass and radius of the star. And in case of dark matter halo, we will see an opposite case, so increase of the maximum mass without the mass radius. With dark matter halo configuration, we could explain the secondary component of GW190814 as a binary merge of dark matter with compact star and black hole. And also I said you that in the more central part of the galaxy, the dark matter fraction is much higher. And then by changing the position of the neutron star, like you see a neutron star from the galaxy center until the age of our galaxy, we could see a change in the properties of the compact star. So we could see a modification of the mass, radius, time of the probability, surface temperature, and so on. So to spot the effect of the dark matter, we have to look on the compact star from the center, the most central part of the galaxy until the age of the Milky Way, and to look on the different properties like mass, radius, time of the probability, and surface temperature. Also, there could be like different smoking guns for the presence of dark matter. The first of them is by measuring mass, radius, and the moment of inertia of the neutron star with 3% of accuracy. With this, I rely on the present and future radio telescopes and the X-ray telescopes. So from the radio telescopes like NIRCAT, SK, and so on, that plan to increase the pulsar timing and discover more pulsars in the galaxy center. We hope to have more information about pulsars in the galaxy center. From space telescope like NICER and NXTP, these are the X-ray telescope that will measure mass and radius of compact star with 3% of accuracy. So they will look at the different compact stars in different locations of the galaxy. Probably they will see the difference in the mass, radius, and time of probability, and so on. If we will look in the most central part of the galaxy, we would see a mass and radius reduction or increase of the mass and radius in comparison to compact stars next to the sun. Another smoking gun is the mergers of compact stars or compact stars in the black holes. So the idea is to look for any kind of modification in the kilonova ejector, gravitational waveform, to look for the effects of the dark matter. But for this, we need large statistic of neutron star to star mergers, neutron star black hole mergers, with the next run of gravitational wave telescopes. And what we have to look on the supplementary peaks in the characteristic gravitational spectrum, some exotic waveforms, modification in the kilonova ejector, and also on the post-merger regime with the next generation of gravitational wave telescopes. So next generation of gravitational telescopes like Cosmic Explorer and Einstein telescope, we hope we'll be able to probe the post-merger phase. And in the case of dark matter core especially, we expect to see any modification of the another smoking gun is by detecting the object that will contradict with our understanding. For example, as a potential candidate that is contradicting to our understanding is the secondary component of GW190814. And the last two smoking guns is the increase or decrease of the surface temperature of a neutron star towards the galaxy center, so heating or cooling of compact star. And last one is a modification of the pulsar pulse profile or extra light bending due to the presence of the halo. So for this, we have to look precisely on the tiny microlensing effect of light bending. It could be also the smoking gun in the presence of that effect. Thank you for your attention.
Thanks, Violetta, for this very interesting talk. So guys, there were plenty of questions, but we still have 5 minutes. So if someone wanna ask something?
I have a question, but if someone else, yeah, please go.
Yeah, I have a question. So I think I have several, but let's start with one. So yeah, right here in the conclusion. So I have a sort of a question about the case of the dark matter halo mostly, right? and it's about the possible generosity measurements. So, for example, because you say that you need high precision measurements of the mass and the radius of compact stars in that case, but if you have the halo, the measurement of the radius that you are getting is not the outermost radius, the radius of the baryonic membrane. So I imagine that in that case, what you will see if you have dark matter out is a high massive star, but your measurement of the radius will be the same if there was no dark matter there, right? So I guess there can be a generosity with another equation of state.
So you have to do that on the mass. Radius would not be observable. Then you have to look on the mass because the mass will increase, the total the mass that you measure will increase. Radius would stay the same, radius would stay the same, but the mass will increase.
Yeah, but what I'm saying is that probably there's a generosity there because normally it's another equation of say that it's a higher mass or that matter. So I guess you need to, for example, look for the log number or something like that to
The same would be the log is the log number. Yes, this is the problem that we discussed in our paper that we will show you. So we discussed in this the paper that we just put the one card. Yeah, this paper. So in this paper, we discussed the degeneracy between the properties of the strongly interactive matter at high density and the effect of the dark matter. So I said that in the case of dark matter, how we see softening of the equation of state with increase of the fraction of dark matter. But at the same time, we ignorant about the properties of the strongly interactive matter at high density. That's why we're using a softer equation of state and a stiffer equation of state, because we still have this range between 11 and 13 kilometers. So all the equations of state in this range of radius, they are realistic, and we cannot say which one of them is the best one. No. So far, we don't know the properties at high densities. So that's why the effect of dark matter could mimic the effect of the strong interactive matter. This is the problem. So then, like mass, radius, time, and probabilities, they would have the degeneracy. We don't know. We would not say definitely this is an effect of the dark matter or it's an effect of the strong interactive matter properties of high density.
I guess if you have three, you can that's not the generosity. But
yeah, so
in the person three, you can
so mass, radius, moment of inertia, and probabilities, they would all have the degeneracy because they all depend on the compactness. You change mass, radius, change compactness, and you could change this compactness by phase transition to quantum plasma, by dark matter in the compact stars, by whatever, changing the chemical composition.
And how about universality relations like the I love
you.
you? So wouldn't this give some deviation to the standard that are independent from equations of state to a large extent?
So the moment of inertia for sure will be with degeneracy because we change compactness. Moment of inertia.
So these are probit ratios, right?
This
So,
is the
yeah.
So now I want to check the
Right.
relation because
Right.
this is something that people say this is the universal relation.
Exactly,
So it
because it
should-
depends on the equation of state. So if you would see some deviation, then it could be something that it's not the equation of state. But I don't know. If it's,
Yeah, so I was thinking about this, and also the test that like came to my mind is this one to look on the neutron stars like with the distance from the galaxy center. So you look in the most central part of the galaxy, and you look on the compact stars further away. Then you will see effect in the central part of the galaxy, but you will not see effect at the outskirts of the galaxy. So that will be kind of independent test for the effect of the dark matter.
Do you have time or not?
Yes, yes, yes.
Well, I'll just have one question. Well, it's related to the formation. So if the stars have this dark matter on the core, okay, probably it was already there in the progenitor star that gave rise to the neutron star.
Yeah.
So would there be a signature then in the physics of the progenitor star? I understand that the percentage will be further diluted because the mass is larger. But still, if you assume here 5%, if the progenitor star had 5 times more mass, it's still 1% of the mass that could be dark matter. So would have people investigated you know, if there in that star there would be an impact of this dark matter, you know, in the questionnaire state, then you have to take this into account, and therefore, how does, you know, all processes within the star depend on the existence of this dark matter? So as this been.
No, that's what I
But
because it requires this the numerical simulation of the formation of the cloud and how. So I expect the higher it would be the dark matter fraction, the faster the mass would be kind of falling into the gravitational pool. So the faster the star will form. Like I expect this dark matter would create this gravitational pool. But for this, I know that it should be the real numerical simulations of the formation of the star.
right.
And so I
But
know people
I
doing
was-
MESA, but the
I was
MESA.
even
people
thinking
do it.
before, sorry, but I was even thinking during the, say, main sequence star or whatever,
Mhm.
then you have that star has an extra component. The dark matter is already there. So if you study, you know, the luminosity, the temperature, and so on, there's going to be an impact on the star
Mhm.
of that, which might be diluted, as I've said, because the mass is larger. And if the, you know, the dark matter was not lost during the collapse to the. And
Mhm. I don't want to my knowledge, nobody did it.
Can I ask one question? So one question about the dark matter itself. So in the simulations, did you study the properties of the dark matter in terms of, for example, the abundance of this dark matter? Or you just assume that it can be dark matter?
I mean, the fraction, what do you mean by abundance? The fraction?
The relative density of dark matter, to make sure that the particle is indeed a viable candidate of dark matter.
So the question is whether we in agreement with all the other constraints on dark matter particles.
Yes, so
Mhm.
to check if this is indeed a good candidate of dark matter, or if it would lead to too much abundance, to overclosure of the universe, or if it would be too little, which is okay, and be interesting enough for this type of study. And so, yeah, my question was that idea of doing something along those lines.
So I know this map, GF, like this mass range is in agreement with this gas problem with the formation of the large galaxy structure. So we're in agreement with the large scale structure constraints. We also in agreement with the supernova explosion. That was supernova in 1987. There was the flux of neutrinos measured, and from the flux of neutrinos, there were the constraint on the cross section of dark matter and the baryonic matter estimated. And we are in agreement with this. This is the upper limit 10 to the minus 45 centimeters, so minus 2. We are in agreement because if we add this small interaction between the baryonic and the dark matter component, it will give absolutely the same result. So we see that we're in agreement also with supernova explosion. And so far, this is what I know. Large scale structure, a galaxy cusp problem, core cusp problem, and supernova explosion.
Yeah, I believe that is all fine. In fact, I was more in the cosmological aspect of dark matter. But I suppose that something actually this leads me to another question. Let's call it question. Imagine I have a model of, as I mentioned before, of stellar neutrinos. It explains the generation of the mass of neutrinos and can explain other problems. And then I have a prediction for a particle. 100 MeV or 10 MeV, something like that. And then I calculate and I say, oh, this can indeed make a good dark matter candidate in cosmological terms. So this does not lead to overclosure of the universe, and the relative density is there, spot on. So there is no need for anything else to explain dark matter. Then how could I was thinking during your talk that it would be very nice to also make this type of astrophysical predictions. So how could I do this? Is there any?
So you would see if you have a neutrino, you would see change in the cooling flux. So then what you have to check is to model the thermal evolution of compact star considering this neutrino. You have to add this particle to the particle content and then to model the schooling curves. And if you're able to reproduce all this experimental data, then your dark matter candidate is in agreement with compact stars.
Okay, it means that I would have to talk to you. Yes. Okay, well, that's nice to know. Okay, thank you.
Okay, guys, I think that's our time for lunch. Let's have a round of applause.